Thanks. So I guess as I was writing these notes, I realized that the first two lectures I'm trying to cover a lot of background material because I don't really know exactly the level at which people are at and where exactly they fit into what they might or might not know about some of these topics. So I'm in particular in this lecture, I'm going to try to summarize 70, 80 years of research into integrable theories, which is of course totally impossible. But I guess my objective here is to just highlight for you some features that integrable theories have that the conventional sort of non-holographic integrable theories have. And I want to highlight those features that we'll see come out very naturally from the 4D Chern Simons point of view. So I guess if you know about integrability, you'll be able to recognize a lot of the formulas that I'm going to be writing down. But I'm going to sort of highlight a few formulas that you should be familiar with. On the other hand, if you don't know integrability, and I expect probably a lot of people here are not experts, I want to just give you a flavor for how these formulas come out. So, this lecture in particular is not going to be very detailed and sort of self-contained. I've provided a reading list for this. There's a lot of really excellent reviews and textbooks and papers on the subject. So that's probably where you can find more information. But just before we get stuck into the detail, I thought maybe it's helpful just to have a quick summary in case in the middle of the lecture you're wondering why I'm emphasizing a particular point. So what I'm going to talk about today in this lecture is essentially integrable 1+1 dimensional theories. So 1+1 for us will be the worldsheet. And the typical example that we'll think about is the principal chiral model on S3, on a free sphere. And the thing about these kinds of integrable theories is that as well as the local charges, they have a whole bunch of extra non-local charges. And I'm going to label these throughout as Qn. N equal to 0 are going to be the local charges, the nether charges. So for S3, this is, for example, the SO4, as we discussed in the last lecture. But there was all these higher non-local charges, which really constrain the dynamics of this system. So in a quantum theory, it turns out that these charges, these higher charges, transform non-trivially under Lorentz boosts. And so this is quite unusual, right? It's not something that we see in higher dimensions. And in particular, I'll try to argue that, for example, the first non-local charge, I'll give you some expression for it soon, but the first charge, if you boost it with a Lorentz boost, you get on the right-hand side, instead of 0, you get the local charge, Q0, times the coupling constant. Now, so that's going to be one of the important equations that we'll see. What we'll also see is that even if you wanted to consider, so if we have some state made up of excitations, so think of some plane wave excitations, and let's say it has 2 excitations, then these non-local charges are going to act on the first excitation, and they're going to act on the second excitation. But what's quite strange is that they'll also have this tail, as it's sometimes called, where you see the first non-local charge, acts both on the first excitation and on the second excitation with the one charge lower, with the local charge. So you might have thought, I don't need these extra charges. I'm just going to consider some Hilbert space in my quantum theory where all these extra charges have got value 0. Okay, so you start off like that with single plane wave excitations and some free theory. Now you go and do perturbation theory, and you discover that unfortunately, or fortunately, that you cannot eliminate these extra charges, because even if this action here was trivial, you obviously want some non-zero Nefer charges, some non-zero local charges, otherwise your excitations are not very interesting. And so when acting on two particles, these non-local charges appear straight away. So the message here is integrable theories like the sigma model on S3 have got non-local charges. These non-local charges transform non-trivially under boosts, Lorentz boosts, on the worldsheet, and you cannot get away from studying them. You need to include them simply because when you're acting on two particle states, they just come out, even if you want to get rid of them. So these higher charges are actually quite beautiful, because what they allow you to do is, and this is sort of a impressionistic equation here. To write it down fully requires a lot of detail, but roughly speaking, what you want is that the scattering of excitations preserve these extra charges. Not only do we want Q0, the local charges, to have to commute with the S matrix, but we want all the higher charges to commute as well. And that really fixes the S matrix, or places really strong constraints on the S matrix. So that's another lesson we're going to learn. And the final thing that we will learn, hopefully, is that it's useful to think of the S matrix as a perturbative expansion. And this is this derivative expansion that I was talking about in the first lecture, where you start off with just a trivial S matrix. So there is no, in the free theory, you add some interactions order by order and momentum, and you get some corrections to the S matrix. And the beautiful work of Drinfeld, which initiated this point of view, tells you that you can write down explicit expressions in these sigma models for this S matrix in terms of these higher charges. So that's, in a sense, if you want, why the higher charges are going to be useful. Okay, so that's my 5-minute summary, something like that. So if people want to ask questions about this, please do. Okay. So I'm going to go into some of the detail now. And we're going to think about integrable sigma models. And you can ask yourself, why do we have all these extra charges? And this ultimately is really just coming from the special nature of 1 + 1 dimensions, right? 1 + 1 dimensions are really quite weird, right? There's all these extra things like bosonization, like T-duality, like if you have a scalar on a circle and you fix the radius to be just right, you suddenly have an SU2 symmetry appearing, current algebra appearing, and so on. So there's all sorts of weird and magical stuff that happens in 1 + 1 dimension. And these extra conserved quantities that we're about to find about are part of this kind of special 2D thing. Okay, so let's start slowly. I've tried to do a sort of mixture of material that can be a little simple and a little more advanced. So let's start a little bit simply. Here are my worldsheet coordinates, x0 and x1, or tau and sigma. And we're going to take a group element, just like we did in the first lecture, which takes values in some Lie group. So the action you can write down for the principal chiral model is just of this form. You can rewrite it in the following way. So you can insert this guy here, which is identity, and you can move the G to the other side because the trace is cyclic. Finally, the one trick I want to kind of introduce very slowly, because I guess if there are some younger students here, maybe if they haven't seen it, then a lot of the formulas can be confusing, is, G - 1 times G is the identity. If you differentiate the identity, you get 0. And now you can just use Leibniz rule to relate the derivative of G inverse to the derivative of G. Okay, so this is just a trick that I'm going to use over and over again. You can use it not just with the derivative, but also with the variation in exactly the same way. So finally, we arrive at an action for the principal chiral model, which probably you will recognize from the previous lecture. It's trace JJ. And this is not in the coset case where we had G mod H. Here, we just have G. So we have a trivial coset, and that's why we have the full J. Okay. So we can try to work out what are the equations of motion. And here, I guess I just do the simple variation, right? I vary the first term. There are two identical terms like this. And I use the nice trick that I showed you here to rewrite the variation of G minus 1, to rewrite that in terms of the variation just of G. And the second term I vary, and I get a derivative of a variation, so that term I'm going to integrate by parts. Okay. Now, I integrate the second term by parts. You see now the variation has got no derivative, and the derivative acts on everything else. And in the first term, underlined in green here, I have what is actually the derivative of G inverse. So using these Leibniz formula that I had here. Okay, now we're almost done. This derivative in the second term can either act on G inverse, in which case it'll cancel the first term, or it can act on all the other stuff, on all this stuff here, in which case we end up with this term. Now, at this point, we're going to use the fact that the trace in our action is complete. Namely, it's a non-degenerate form on the Lie algebra. Here's a Lie algebra element, here's another Lie algebra element. There's a completeness of the trace. If we want this expression to be equal to 0 for all variations, the only way to do that is to say that this second term has got to be equal to 0. And that's how we arrive at the equation of motion. Okay. As an exercise, you can also show that there is a second version of this equation of motion where you have G minus 1 dg instead of dgg inverse. So you can ask me about that on Slack, how to get that. Now, the way these equations are written down is they're written down as currents, as current conservation equations, right? This guy inside the bracket is a Nefer current. Here's the left Nefer current, and here's the right Nefer current. And you can derive, again, the Nefer current conservation laws instead of from the equations of motion equivalently, right? In the usual way, you can derive them from multiplying from the left or from the right by a constant group element. So this is another nice exercise you can do. And these currents, you expect to see them, right? So for example, if I was doing SU2 as my group, then I would get an SU2 times SU2 symmetry. And that's, of course, SO4. But SU2, as you all know, is S3, the free sphere. And this is the symmetry SO4 of the round free sphere. So that all fits very nicely. So these are just conventional symmetries of the target space that you might expect to have. What is now, we sort of shift gears, right? This kind of thing I could do with any in any dimension, sigma model, for example, and I would find such conserved quantities just from the symmetries of the target space. On the other hand, what's special here in 2 dimensions is that not only are these currents conserved, but they're actually also flat. So let's see how that goes. So I'm going to take my current, and I'm going to think of it, just to make this calculation simple, as a 1 form, right? So this is an exterior derivative now. It has a component d tau, and it has a component d sigma. And I'm going to take an exterior derivative of that, so I will end up with a 2 form. So with my Leibniz rule, d acts on g minus 1, or it acts on dg. D squared is 0 because it's an exterior derivative. And here I use again the same trick that I did before of changing the G derivative into a, a derivative of G inverse into a derivative of G. Okay, so now we have a left-hand side and we have a right-hand side. And if you put the right-hand side, flip it over, you get this flatness condition known as the Morikardam equation. And that's just true. These currents satisfy this equation, as we've just proved. Right, this is a covariant derivative here with respect to, if you want, the connection JR. So in components, I've written it out here in case it helps you clarify. You see the structure constants of the Lie algebra up here. Okay, now it's precisely the flatness of this connection that allows us the flatness of these currents, rather, sorry, that allows us to find extra conserved quantities. So I want to do a little calculation again, which is going to get you halfway there, and hopefully you'll be able to complete the calculation to see how you get these extra conserved quantities. So let's take a really weird looking expression. We take the zeroth component of the current in the tau direction, and we integrate it, I suppose, from minus infinity or from your favorite point. We integrate it all the way up to some point. Now, if you take the exterior derivative, and you can do some simple manipulations as follows. So you take the exterior derivative. Here is the d tau component. Here is the dx component. And we act with d0. And when we differentiate with respect to the spatial coordinate, well, of course, that just gets rid of the integral. Now we use the fact that this current is conserved. So d0, j0 is the same as d1, j1 up to a sign. And you end up with this expression. And this expression is precisely the Hodge dual of the one form J. So look, this is quite strange, and we've used the fact that not only do we have a conserved current, but we've used the fact that we're in 1+1 dimension. We've taken a non-local expression, we've applied d to it, and we've gotten star of the current. So this is the non-trivial part of the following calculation. Now you can go away and at home check that if I define a new current in terms of the old current, star of the old current, times this weird non-local guy, times the old current J mu, that this J hat is again conserved. And over here, I've done the hard bit. So now you just plug it in and you very easily check that this J hat is conserved. Let me just pause here and see if people have any questions. Okay. So once you have this current, of course, it's conserved, so you can write down a charge for it. The current involved some non-local piece, some integral, and the corresponding charge also involves now a non-local piece. Now we integrate not just, see that this is just the local piece over here that comes from the current, but there's a non-local piece which involves a double integral. Right? And that's quite strange and unusual. And that's really at the heart of this whole integrability in sigma models. So I've done this very, very slowly on purpose, just so you can see what the currents look like quite explicitly and what the first non-local charge looks like. So this Q hat I'm going to call throughout now Q1, the first non-local charge, and Q0 is just the local charge. And in fact, we can do much better and sort of much more elegantly than going through all this kind of hardcore explicit integral formulas, but we can do it as follows. There's an infinite tower, in fact, of conserved quantities. So how do I find them? Well, suppose I give you some current which is conserved. Because I'm on a, let's also be on a flat world sheet, so R2. Well, that means this conservation law means that you can write the current in terms of a potential, right? The derivative of a potential. So this is just star d chi. Okay, but then the claim is that I can define a new current, which is a covariant derivative of the potential. So instead of being star exterior derivative, it's a covariant derivative. And the covariant derivative, okay, is just defined like this in terms of J being the connection. And you can check, again, very simply, that this new current is also conserved. So how does that go? Well, here is the n+1 current. I'm going to differentiate it to see if it's with D to see if it's flat. Okay, it's defined in terms of a covariant derivative D. And there are some exercises here where you can check that the flat D and the covariant D commute with one another. So I can switch the order. And now I have D of the potential. So I go to this equation and I replace D of the potential by star of J. And now you see the nth current was also obtained from some n-1th potential in this way here. So I insert that instead. And the second exercise shows that these two Ds, they actually commute with one another. And so this part here is symmetric in mu nu, this part is anti-symmetric in mu nu, and so you get 0. So the exercise here to check that the normal derivative, the conventional derivative, and the covariant derivative commute, that translates to the equation of motion, which we always have. But the second equation comes from the Moret-Cartan condition, the flatness condition. And so that only happens in these special cases. So starting with a potential which is just identity, the first current at level -1, the first current we get is the local current. Then at level 1, we will get the first non-local current. So J1, roughly speaking, up to some local piece is the same as this current J hat that I defined. And you can keep going. And every time you go up one order, you end up with less and less local. So you start with 2 integrals, 3 integrals, 4 integrals. You end up with less and less local charges. Okay. So all these charges, you can formally just add them up and write them down as a generating function. And for some reason, well, I guess we can't go into too many details, but people like to expand it around infinity. Okay. So you have some arbitrary parameter u, and you add up all the charges with the power of u the same as minus k-1 for the kth charge. It's just conventionally done like this. You could do it around any other point, but this is what you often see in textbooks. And this guy here, well, of course, it's a matrix, right? Because all these charges, they're Lie algebra valued, right? Like, for example, this charge was SU4 of a principal chiral model on free sphere was SU2 times SU2 charge. And so all these higher charges also take values in that Lie algebra. So it's a matrix, and we call it the monodromy matrix. Okay. So what I want to do now is I want to show you how you can obtain a much nicer expression for this monodromy matrix in terms of a quantity called the Lax connection. So, I mean, this is a perfectly good formal definition, but it would be nice to come up with some slightly better, slightly more geometric object. So here's what we're going to do. We're going to define this connection, or this one form L, and I guess this is a sort of slight sort of cooking recipe, if you want. Is these factors you have to choose them in this way, and if you start with general, the way I could derive this is I could start with some general factors in front of J and in front of star J. And then we would go through the whole construction and see that you need the factors to look like this and like this. But let's just take these factors as they're given. And why do we want them to be like this? Well, when you do this, you can define this kind of Lax covariant derivative. I'm going to try to call it curly D, right? And what's nice about this is that this is a flat. This Lax connection is flat. Now, I want to show you explicitly how that works. So I'm going to calculate the commutator d mu d nu and see that this is equal to 0. So let's plug in. We're going to get some terms which are just proportional to 1 power of j. Here is the first term. And we're going to get some other terms which are proportional to the commutator of j with j. Okay. Now, in fact, if you do this in a little bit more detail, you also you see that you get terms which are proportional to star j. But that's okay. You can include them, and there are terms which are the commutator of star j and star j over here. Now, the mixed terms, the cross terms in this commutator, actually, you can check they cancel one another. So after the dust settles, and when you use relations like star star is equal to 1, and you rewrite this guy, so d star is equal to the interior derivative d, after the dust settles, you get this expression here. And I've underlined in green the terms that combine to give you 0 as long as the Moret-Cartan equation is true. And the terms in yellow, which are 0 as long as the equation of motion of the original sigma model is satisfied. So this Lax that I've sort of introduced fairly arbitrarily is flat, gives rise to a flat connection, as long as the original sigma model that I had as long as we satisfy the equations of motion and the Moret-Cartan equations of the original sigma model. So in other words, as long as we have a current which is both conserved and satisfies and flat. Okay. Now, at this point, you might be wondering, why am I introducing such a weird auxiliary problem, such a weird auxiliary connection? But remember, what we're trying to do is, we're trying to find some nice expression for this monodromy matrix, for this matrix that generates all the charges, all these extra conserved charges. So if you have a flat covariant derivative, namely one where the two d's commute, you can define an auxiliary linear set of partial differential equations. So we can try to find functions phi, which now are not only functions of the coordinates, but also of the auxiliary variables, which we call a spectral parameter, that appeared in our Lax, right? Here it was. And we can say, okay, I want to solve these equations. And in general, you see, mu is equal to tau or sigma. So you would have two equations for one function phi. So in general, this wouldn't work. But because the two d's commute with one another, these equations are actually consistent with one another. So you can do that. You can ask for such solutions. And a formal solution, well, you know, it's a first order equation, right? So formally, we can write it as an exponential of something times some constant. And this is what we do formally, right? But of course, everything is a matrix now. Everything is matrix valued. So you have to be a little bit careful, and you have to do a path ordered exponential, which you write down like this, and you can choose, and often we just choose to have L1 inserted here. So I'm really solving the equation d1 phi is equal to 0. And I'm solving it formally, right? I don't actually know what this path ordered exponential looks like if you gave me a particular solution, but formally it exists. And in certain very simple cases, I might be able to write it down. But basically what's going on is when I act with the covariant derivative on this t that I have here, well, I differentiate, or I do the lax, so that's just the definition of a covariant derivative, but the derivative of this path-ordered exponential, sort of by definition, just brings down 1 power of the lax, and so you end up with 0. And you don't need to solve the de-zero equation in some sense because it's compatible. The two equations are compatible. Okay, now, all of this is just some game that we are playing given a current that is both flat and satisfies the Moré-Cartan equation. But now comes the nice part. Now you can consider the limit where you send these parameters. So when I was writing down my solution, I was integrating from some initial time to some final time. Now I'm going to send those to infinity. And I arrive at this expression for this matrix T. And it turns out that that matrix is precisely the one that generates all these non-local charges for you. So I guess in view of the time, I'm going to just leave this as an exercise, but roughly speaking, you can take this lax and you can calculate its derivatives and evaluate them at u equal to 0. So here is my lax, and you can calculate its first derivative and its second derivative and so on with respect to u. And you can show that this monodromy matrix has got precisely the expansion that we wanted. So bottom line is, this encodes all of the charges in terms of some auxiliary connection L1, or L mu more generally, auxiliary Lax connection. And that's how people tended to think about these integrable charges. They tended to think about them as there being, at least classically, there being some auxiliary linear system that Lax just invented, and that you could then express all the conserved charges, all these non-local conserved charges, as coming from this path-ordered exponent. So I don't know about you, but I guess for me, this was always very mysterious. You know, it was sort of a recipe. Okay, it worked. We can go and check, and it really works. It's true. But why does it work? Where did all this stuff come from? Where did the spectral parameter u suddenly, you know, I sort of pulled it out of a hat, really. I just presented you with some expressions. Yes, they work, but what is the meaning of this parameter u and so on? So these are all sorts of questions that I hope we'll be able to answer a little bit tomorrow. But for now, I guess we're just going to carry on with our overview. And I'm going to ask what happens. Okay, so let me pause here maybe and see if people have questions.
Yeah, maybe a question. There seemed to be an ambiguity by a constant when you define the charges with an integral that you set to -infinity, the lower end of the integration. What changes if you change that constant? In particular, if you try to, for instance, define the charges on a compact circle, say, instead of on a constant time slice, does this constant come up?
So classically, you know, I could quite happily define them on a circle. There wouldn't be a problem. It's quite subtle what happens in the quantum theory, and so the question about whether or not these charges are conserved in the quantum theory and whether they are conserved when we go to a compact direction, sort of wrapping, when there are potential wrapping corrections, can be quite subtle. And I guess you have to sort of go case by case and use other methods to figure out whether these things are preserved in the quantum theory. There was a question about, does this all carry over to the WZW model in 2D? So formally, yes, but it's nicer to think about a family of integrable theories where you have a principal chiral model piece and a WZW piece, but with arbitrary coefficients in front of them, in front of the two terms. And that whole family is classically integrable, and the Lax connection is kind of trivializes precisely at the WZW point, because the currents there are really left moving and right moving. So really the Lax connection, all it does is it just encodes the fact that you have a chiral theory on the world sheet there. But if you consider a whole family of theories with two arbitrary couplings, then you can write down a Lax that's kind of non-trivial when you have those two parameters. So I'll try to put up something on Slack. There was a paper by Kostya Zarembo and the second author whose name escapes me at the moment, but I'll put up on Slack a reference to some work on in that direction. Okay, any more questions?
There is yet another one in the chat.
Okay, so what does auxiliary mean here? Auxiliary means I just pulled it out of thin air, right? This I'm trying to solve some completely unrelated partial differential equation, it looks like. That's what's crazy, and you should be surprised. This phi, this capital phi, which I solve here, it has nothing to do with the sigma model, right? It has no relation to the sigma model at all. It's just some arbitrary guy. And yet, solving this equation in terms of this monodromy matrix encodes all of the charges of my theory. And there's a way, I'm skipping over a whole bunch of material, but once you know this solution, you can then work hard and figure out what is the corresponding solution on the sigma model, at least classically. Okay, more questions? Yeah, please keep stopping me and asking questions and interrupting. That's very helpful. Okay, so I'm going to sort of mostly summarize now on what happens when you ask the question. You know, you've got these non-local charges. You could look at the Poisson brackets of this theory, and you could ask what happens under Lorentz transformations, just classically in terms of Poisson brackets, to these charges. So one thing classically that's kind of straightforward that you really expect is that the local charges just Poisson commute with the boost. So remember, just let me very briefly say that if we're living in 1 + 1 dimensions, there's this really nice picture, of course, where the boost is just a rotation in the xt plane. So the local charges, they just Poisson commute, great, with the boost. And similarly, you can show that the higher charges also Poisson commute. So, you know, this is a hardcore calculation of working out all the Poisson brackets and figuring out how that goes through, but it does. So people did this, they worked hard, and they showed that the boost also Poisson commutes with, for example, the first non-local charge. What's much more interesting is what happens in the quantum theory. So in the quantum theory, okay, you can show that the boost commutes with the local charges, but that there's this really intriguing relationship between, for example, the first non-local charge, and the commutator of that with the boost gives you back the local charge. And h here is the coupling constant. Okay, don't worry about some factors of 4 pi I, doesn't really matter. But c is the quadratic Casimir. So if I turn off my coupling, then I just recover back the classical answer. But turning it on, you sort of get I don't want to call it an anomaly, but you get some quantum corrected term. Now, how does this happen? There's a very nice picture that I guess was developed by Bernard, maybe with Leclerc as well. And the idea is like this. You see this first non-local charge, the one that I was calling Q hat, it was written as a double integral of current. And if you're in a quantum theory, when you have two operators sitting at different points, that's fine. But when those points come together, you could have some singularities. So when y goes to x, actually the currents, it's well known, right? The OPE is non-trivial, and it looks like this, right? So you might recognize such an OPE just from a WZW model, JJ. Oh, someone's asking about the factor of 4 pi I. You'll see just in the bibliography, I give a reference to a very nice review of this material in much more detail, and I think that they look after that factor of 4 pi I. But yeah, you're right, it does come from some sort of residue, and I'm going to try to give you a little flavor for how that appears just now. But you know, all I really am hoping that you get from this is that when you try to work out what is the commutator of the boost, which is a Lorentz symmetry with a first non-local charge, that you get something that is non-zero on the right-hand side, which is the first local charge. Okay, so as I was saying, this in the quantum theory, the problem with a bilocal charge, something that's defined in terms of two integrals, is that the integrands might come at some parts of the integration region, they might come close together. When they come close together, the OPE is singular and looks like this. So let's consider what this boost does to our charge. Not sure what that was, sorry. What this boost does to our charge. So you see we have, I'm just going to draw one of the two contours here in green on the left-hand side. And the way you have to evaluate it to avoid this singularity is you have to regularize by some sort of point splitting. So you separate them out, you keep delta bigger than 0 until you finished with the calculation, and then you send delta to 0. So when you do that, and you say, what does the boost do? Well, remember what I mentioned is that the boost is like a rotation in the xt plane. And if we boost by 2 pi, we do a 2 pi rotation. So this contour gets kind of bent around the point x, because we're doing the rotation around x. And now because everything is written in terms of these currents, and these currents are flat and conserved, then you can split up the contour, right? It doesn't matter, the shape of the contour doesn't matter. And indeed, as the question was asking, this contour over here is essentially can be written as just the previous contour that we had on the left-hand side times a residue contour around the circle, and you pick up this OPE residue here. So that's kind of, I'm going to pause here again and let people ask questions, but that's kind of the idea of how you derive this kind of relation. Okay, so we've learned sort of, or I've highlighted maybe is a better way of saying it, this kind of lesson, that you have non-local charges in these sigma models, and that the boost gives you these funny relations where it doesn't commute with the non-local charges, it gives you some non-trivial right-hand side. And we'll see that appearing that's a sort of typical feature of Youngian integrability. And the other thing I wanted to highlight was that if you have this non-local charge, here it is again, okay, I didn't write down the local piece here, but if you just look at the non-local piece, and you imagine that you want to figure out some sort of semi-classical analysis of some magnons or some excitations in your world sheet theory. Okay, so I'm going to put my magnons far apart. They're essentially free particles. Let's see what value this charge, this first non-local charge, for example, has. So what you can do is, right, this integration, you're integrating over the whole real line, and you're doing it twice, and the integration region will split up into essentially 3 pieces. One where the integration is in the neighborhood of the first magnon, of the first excitation, let's call it. Another piece where both of these integrations are near the second excitation. And then there is a part where you're integrating the x over here and the y over here. And so these two regions, well, they just tell you that the charge acting on these two excitations acts as a sum of the charge of the first excitation and the charge the charge of the second excitation. But then, so that's sort of exactly the same as you would have if you had a global symmetry, right? If you just had a global symmetry and you had two excitations, then you would just add up their SU2 charges to get the total SU2 charge, for example. But what changes here in this non-local charge is that you have a region of integration where you're going to pick up a sort of a tensor product of the local charges. See, because the non-local charge is an integral of J and another integral of J. And when you're integrating over different subregions, this just becomes a local charge, right? An integral of J is just a local charge. So here you have like this tail appearing, often called the tail. And so you have this very nice semi-classical picture that these non-local charges have this kind of, it's called a non-trivial coproduct, which means that when they act on two particle states, they're not just the sum of the actions of the first and the action on the second state, but there's this funny mixing happening that's sort of non-trivial. And this is exactly how the Yangian appeared in Drinfeld's first realization, if you look at his papers there. And this is sort of the physical way in which this tail manifests itself. So what's important about this formula is that, well, even if you did act with, suppose that you didn't like these charges Q1, and you said, okay, I'm going to set them to 0. Well, by the time you have a multi-particle Hilbert space, you couldn't get away with setting the higher charges to 0 because of this tail. So when you have more than one excitation, you have non-trivial, you have to have these higher charges being non-trivial. And so you really have to be asking the question, okay, I'm looking for representations not just of the Lie algebra, but of this full Yangian algebra of higher charges. Okay. So just a sort of concluding thought, I've been talking about the principal chiral model here. Benner, Polchinski, and Royban showed that the Metsayev-Zeitlin superstring, this superstring action that I wrote down for you, the one that was J2, J2, J1, J3, can be written in terms of a flat Lax connection as well. And now this flat Lax connection looks a bit more complicated, and I'm writing it in terms of Z rather than U, but that is the spectral parameter that we have. And so unfortunately, this is something I have to leave as an exercise for you, or you can look through the review by Arutyunov and Fronov to see in more detail how that calculation goes through. But basically at the classical level, there is a Lax also for the Metsayev-Zeitlin string. And so when people learned that, when Benner, Polchinski, and Royban showed this, I guess there might have been a lot of excitement from the integrability crowd because they would have said, well, that's it, right? We should just apply this Yangian machinery to find what is the corresponding S matrix of this sigma model, of this string theory rather. But unfortunately, the story is not that simple for the superstring. And that's because, you see, I guess this sort of refers a little bit back to the question that Sasha asked in the first lecture. The string theory has got this kappa symmetry, and you can't just in the quantum theory leave that alone. That's an extra gauge symmetry that your theory has. And you need to gauge fix that symmetry before you can write down expressions for physical states, for scattering of physical states, for charges acting on physical states. And when you fix the kappa symmetry, you break 1 + 1 dimensional Lorentz invariance, and you end up with some messy, integrable, but non-Lorentz invariant theory. And unfortunately, the sort of direct machinery that you might have used from Drinfeld and from others doesn't directly apply. But there's this sort of tantalizing connection to the classical Lax, and one of the things that hopefully one can try to understand a bit better, maybe using this Chern Simons approach, is how to quantize this in a covariant way. So how to recover this nice Lax integrability in a quantum sense. Okay, so please, it's a good time to ask some questions. I'm hoping, Shota, I have maybe another 10, 15 minutes.
Yeah, you can. Yeah, 15 minutes or so.
Yeah, I'll try not to be. Again, I'm trying just to highlight some features of integrable theories, so that when you see them, how they start appearing in the Chern Simons theory, you can say, oh, okay, there, I saw that in the integrability. Okay. So I guess any integrability lecture has got to discuss the Young-Baxter equation, and so here's my very brief attempt at doing that. So a Young-Baxter equation is a very general equation, and you can think of it as having as telling you a little bit about how excitations scatter from one another in an integrable theory. So you could set up an S matrix type calculation where you have two plane waves or n plane waves in some distant past, and then they go to a distant future, they scatter one after another, and you end up with a different, with the outgoing state. And so this of course, as we know just from quantum mechanics, this ratio is just the S matrix of how these two plane waves scatter past each other. Now, in 1+1 dimensional integrable theories, we saw there are all these higher charges. Okay, I didn't show you, but these higher charges are actually commuting with one another. And so that means that if you set up some in state before scattering, then it has some particular conserved higher charges, an infinite number of them in principle. Certainly a finite number of them will be non-zero. And then when you scatter through, the outgoing states better conserve all these charges. And that's really a very strict criterion. Not only is energy and momentum conserved, not only as well as any kind of internal global symmetries, Nefer symmetries, but all these higher conserved quantities have got to be conserved too. And what that means is that there is no particle production in this scattering. So it's always essentially 2-to-2 scattering. And the only thing that can happen is that the momenta, as well as the global charges, can just switch between particles. That's all that can really happen. There's some kind of time delay, and that's all that happens in this scattering. And the beautiful thing is that this process, therefore, has to factorize. So if I start with 3 states, for example, then they'll scatter with one another, okay? And all that can happen is just 2-to-2 scattering, like I said. So here's one way in which this 2-to-2 scattering can happen. You can first scatter 2 and 3, then you can scatter 1 and 3, then you can scatter 1 and 2. So I'm thinking of time going up this way. But someone else might have in a different Lorentz frame or something, they might have seen the scattering as being first R12, then R13, then R23. So I guess I realize now I'm switching from the S matrix to the R matrix. It's just conventional in this integrability setting to combine the S matrix with a permutation and call that the R matrix. It doesn't really matter. Permutation just switches the two indices. So whenever I say R matrix, you can think of S matrix as well. And now here are 2 different ways for this process to happen, but the final answer better be equivalent, right? So the final out state shouldn't be able to distinguish in which order I did these. I mean, after all, the order could depend on the observer. So that translates into an equation for the R matrices, for these 2-to-2 R matrices. And this is called the Young-Baxter equation. Now, typically, these plane waves, they live in some representation of some Lie algebra. So when we were doing so for example, they would live in SU2 times SU2 or SO4 if we were doing the principal chiral model. So the Young-Baxter equation is really a matrix equation, and you should really think of the R matrix as this matrix that glues for you two representations and spits out two other representations. And the fact that it preserves symmetry just means that it commutes with these local charges. So it preserves the local Neff-symmetry, I should have said. The global, sorry, not local, the global Neff-symmetry. Now, this condition places some restrictions on the R matrix, but actually we will have more restrictions, and this is how they come about. So in 1+1 dimensions, the on-shell condition, it's traditional to write it, you can solve the on-shell condition in this way, so you can have the energy to be cosh of some rapidity u and the momentum to be sinh, so that this satisfies the usual on-shell condition. And in terms of this rapidity variable u, what's quite nice is the boost operator that I introduced in the previous set of notes just acts as a shift on this rapidity variable. Okay, so this rapidity variable is quite nice. The boost acts as a shift, and the S matrix, of course, can only be written because of momentum invariance in terms of the difference of the two U factors. So if I plug in this expression for two-dimensional momenta, Pi and Pj, then you can very quickly check that this is the same as cosh squared of Ui minus Uj, so it's just of difference form. And Yang, all those years ago, showed that the R matrix, one simple solution to the R matrix, as long as, for example, you're in the representation of a fundamental representation of SUN, looks like this. Okay, so it's an identity. So this is a 2x2 matrix on sites I and j. It either acts by identity or it acts by the permutation operator. And those are the only choices that are consistent with the SUN symmetry. And something that I will not talk about here in these lectures, but there's an overall factor out front, which always is there. If you're solving the Young-Baxter equation, that's a matrix equation. The overall normalization is not determined. We could do a whole course on how to determine that normalization. But for us, what's important is this matrix form here. And in particular, what I want you to notice is that the permutation, that the permutation matrix can be written as a quadratic Casimir in terms of the generators of the Neff symmetry, of the global symmetry. So it's a nice exercise that I've left it here for you. Just plug in this into the Young-Baxter equation and check that it holds. Now, there's a whole industry, right, of looking at the Young-Baxter equation, finding a particular representation, and seeing what other solutions you can write down. I wrote down here the simplest solution that Young wrote down many, many years ago. But Drinfeld thought about a sort of semi-classical limit of the R matrix. So he said, let's consider an R matrix which starts off as 1, so there is no scattering, and then there's some correction, and there's some quadratic correction, and so on. And the Young-Baxter equation then reduces to this kind of, at leading order, so this is at order h squared, it reduces to this condition here, which is a Lie algebra condition, really. And he showed that that can be uniquely solved by this quadratic Casimir. And then he said, well, perhaps I can generalize this. Maybe I can write these higher corrections, not just in terms of the local charges, but in terms of the higher and higher charges. And so, he wrote his famous papers in which he was able to show that the R matrix takes this form. So I'm writing here the log of the R matrix, just because that has a nicer expansion in H. And here is the classical piece, the one that Yang found. So remember, we had a part that was like 1 plus H over U, TT, and this is this part here. And then here you see the higher charges starting to appear at higher and higher orders. So if we know how to represent these guys, then we'll be able to write down the all orders R matrix. And the basic principle for the R matrix is not to just commute with the local charges, but the R matrix has got to commute with all the higher charges. Okay, to do this sort of precisely, you know, I would have to introduce the notion of a Hopf algebra and coproducts and so on, but this is the general idea. And the final thing I want to tell you about is something called the evaluation representation, which we'll see a lot of tomorrow. And that's, Drinfeld showed that if you start off with some representation of the Lie algebra, then some of these representations under certain conditions lift to a very trivial representation of the Youngian, where you just say the higher charges, I wrote down here Q1, but all the higher charges are equal to 0. So this doesn't hold for every representation of the Lie algebra, but for example, for the fundamental representation of SU2 or SUN, does hold. And so you might think, okay, but this is pretty boring, right? I'm just setting all these charges to 0. But what Drinfeld was able to do is he showed that actually you can then use the boost automorphism to write down a more general representation. Namely, you boost the original representation, this kind of trivial one, and when you've boosted it, you get this local piece appearing. Remember, this came from the fact that the boost with Q1 gives you Q0. So this, if you want, is then a general representation with general rapidity U. And that's something that we are going to see. So I guess all I wanted to highlight is that in Drinfeld's formulation of these things, he gives you a evaluation representation for the Youngian, and where the higher non-local charges appear non-trivially with this boosted piece, with a boost U. Okay, and he uses those to write down the R matrix in this kind of form. Okay, so I better stop here. And if there are questions, please ask.
Okay, let's first thank Bogdan for a very nice lecture. And are there any questions? Oh, by the way, Sasha, can you make Henry co-host?
Yes, I will do that right now.
Okay. So while we are doing that, so are there any other questions? Well, let me ask one question then. So, so in this lecture, you are basically like emphasizing the importance of Youngian, which is like a non-local symmetry. But in order to show the factorization of the S matrix, we needed to use the local higher conserved charges. Is there like a good understanding about the relation between the two?
Well, did you say local conserved charges?
I thought like the factorization of the S matrix
You just broke off, sorry, yeah.
Yeah, sorry, the factorization of the S matrix follows from the local charges.
Yeah, so I've sort of suppressed that part of the story, but you're right, as well as these non-local charges, there are also local charges that these integrable theories have. What's nice here in this presentation, right, is that if you understand how the Youngian is represented, then you can write down the R matrix and see that it satisfies all the conserved quantity. Sorry, it satisfies all the right commutation relations that the R matrix should have. So those follow from the Youngian relations. Now, there are of course other points of view, and you can indeed, at the classical level, right, we can certainly understand the formal relationships between the local and the non-local charges. Quantum mechanically, this is harder, but I guess I had to pick out a few things that I wanted people to see, and so when they see them in the Chern Simons theory, so here's one relationship that that I wanted to highlight. And here's a sort of another relationship I wanted to highlight. Yeah.
Okay.
There was a question in the chat, sorry. Can I see so to go to the Zumino-Witten model, and how the charges, to the Zumino-Witten point, and how these charges, what happens to these charges when you're at the Zumino-Witten point, is something that there are these famous papers of Bazhanov, Lukyanov, and Zamolodchikov that deal a little bit with that idea. It's kind of subtle. So I think at the level, at some level, yes, these charges should rearrange themselves. How exactly that happens, I guess, is probably a little bit beyond the present discussion. But yeah, those are that. I think that's all I want to say about that.
Okay, oops, there is yet another question. Can you read, Bogdan?
Yeah, I can read. I'm wondering if, in view of the time, maybe
yeah, okay, maybe we can postpone that question to the Slack, probably.
Exactly.
Then.
Yeah. So that'll encourage people to go onto Slack, and then I can try to answer that on Slack because it's a nice question.
Okay, sounds good. Okay, so let's thank Bogdan again, and
thanks.
Let's move on to the next lecture.